Vikings, we're here to talk about gas laws. The first gas law we're going to take a look at is Boyle's law. And Boyle's law is talking about how the pressure and the volume are related. So if you have a syringe right here, right, the top is open, so I can take in air, I can push out air. But if I close the top, and now it's a closed container, I'm going to open it up to about 20 milliliters. If I put my finger over the top and I push it in, so I've cut the volume by half, so I've actually increased the pressure by 2. I've cut it by half, so I've doubled the pressure. So if you cut it by a quarter, then I have quadrupled the pressure. So that's a big difference. That's actually really hard to hold right there. And you actually get kind of to a limit, which explains the graph that we see down here. You get to like an asymptote. And we'll get more into that in a future lesson, but right now we're just going to learn the mathematical relationships with Boyle's law. And so the formula is P1V1 equals P2V2. You don't have to memorize them. We'll get you the formulas. But what we basically have is we have an initial condition here, and we have a final condition. All right? So example number 1 asks for a gas that has a volume of 7.4 liters at 765 millimeters of mercury at 25 degrees Celsius. What volume in liters will the gas occupy if the pressure is increased to 1075 millimeters of mercury and the temperature remains constant? So your initial conditions are, here's your volume, that's V1, here's your initial pressure, and then here is your final pressure. Okay, that's a unit of I go by looking at the units. That's how I tell which one it is. And so we're looking for volume, right? And so that's our second volume. So just plugging the numbers into the formula. P1 is 765 millimeters of mercury, and V1 is 7.40 liters, and then P2 is 1,075 millimeters of mercury, and V2 is our unknown variable. So this becomes the theme. There's 4 variables. You get 3 of them. You have to find the 4th one. So to isolate them, I need to isolate this variable, so I need to get rid of this term my finger's on. So I'm just going to divide both sides by 1075. And so I just do 765 times 7.4 divided by 1075 equals 5.27 liters. All right, piece of cake. That was easy, right? The units will cancel out, and the last unit you're left with is liters. I'll probably start dropping units just because we're not focused on that unless it's important. Okay. So for example number 2, gas with an original volume of 1.5 liters is expanded to a new volume of 4.75 liters and a new pressure of 2.20 atmospheres. Calculate the original pressure of the gas if the temperature was held constant during the expansion. So one other way you can do this is you can write out your information like this. This is totally fine with the final answer, but we have our initial pressure is what we don't know. So that's our X value, right? Now, our original volume was 1.50, and then our second volume was 4.75. Both of those are liters. And then the new pressure was 2.20 atmospheres. Okie doke. So the formula is, just to refresh your memory, P1V1 equals P2V2. So you just plug in the numbers again. X times 1.50 equals 2.20 times 4.75. And again, we're going to divide both sides, 1.50. And 2 times 1.75 divided by 1.5 gives us, x is 6.97. All right. Now, what unit should that be? We got liters and liters here. We got atmospheres, so that should be atmospheres. Okay. All right. So on this example, why does an increase in volume lead to a decrease in pressure? So if we increase the volume, we will decrease the pressure. This is called an inverse relationship. Why does that happen? We want to justify it in terms of actually looking at the particles. So if we take a box that's this volume, and if we approximately double the size of it, okay, and let's say there's 3 particles in here, and then there's 3 particles in here, because pressure is the collisions with the container, will they collide more often in here, or will they collide with the container more often in here? Okay, so you can tell that you get much more collisions with the container right here rather than here if they're kept at the same arrow distance, right? You seeing that? If we keep the temperature the same, the arrow distance is still the same, so they are less likely to hit the container. You seeing that? Okay. So there are fewer collisions. All right, with more empty space. Now, your answer, I can write this because I'm the teacher. Your answer needs to be a full, complete sentence, but I really gave it to you in words because I'm not going to write it all out for you. I'm just going to tell you audibly, and I want you all to kind of make a full, complete sentence. We have more collisions over here. I'm sorry, we have more collisions over here, so the pressure will be greater with a lower volume, or the pressure will decrease with a greater volume. Okay. All right. Now we're going to look at Charles' law. Now I just kind of gave you the theme, so we're going to kind of move on a little bit more. We're looking at Charles' law, where the volume of a fixed mass of gas varies directly with the Kelvin temperature at constant pressure. And I want y'all to write in big letters, must be in your Kelvin. Okay? Must be in Kelvin temperature. Good? Now the formula is going to be V1 over T1 equals V2 over T2 if the pressure is constant. So a sample of gas has a volume of 150 milliliters when its temperature is 17 degrees Celsius. If the temperature is increased to 32 degrees Celsius, what will the volume become, assuming the pressure remains constant? So I'm going to work it out right here. We said we've got V1 and T1, so we've got, now to change it to Kelvin, we're first going to take our initial temperature, right? That was 17 degrees Celsius. To change it to Kelvin, we are just going to add 273. Okay, that's that simple. So 17 plus 273 is 290. Okay. And then we change it to a new temperature. We change it to 32 degrees Celsius, right? So if we add 273 to that, that becomes 305. All right. So you must have the Kelvin temperature. That is very important, or else it will just not work. Just to refresh your memory, we've got V1 over T1 equals V2 over T2. So our initial volume was 150 milliliters. So around 150 milliliters. And we'll divide by our initial temperature, which was 290 Kelvin. We want to know the new pressure, the new volume, if we increase the temperature to 305 Kelvin. All right. So this is just a number we can type in the calculator and find out. Now we need to get rid of this. This is division, so we're going to do the opposite. We're going to multiply by 305. Multiply by 305. Okay, the 305 is going to be the numerator there. So I'm going to take 305 times 150, and I'm going to divide by 290. And so my new volume will be 158 milliliters. Great. Example number 4. A balloon is filled with a gas at 250 degrees Celsius to a volume of 5 liters. What temperature in Celsius would the gas have to be changed in order to cause the volume to drop to 2 liters, assuming the pressure remains constant? So, if we are going to take, we started with 25 degrees Celsius, right? So another thing I like to do is whenever I read it, I know I'll have to convert it to Kelvin, so I'm going to cross it out. And so I'll take 25 and I'll just add 273. Okay, and that's going to be 298 Kelvin. All right. That way I don't have to worry about that. And the volume is going to change from 5 liters to 2 liters. So my initial volume was 5.00 liters, and it had a temperature of 298 Kelvin. So now what would be the new temperature if I change it to 2 liters? Now this gives a lot of students trouble whenever the variable is on the bottom. So an easy trick is just to flip them. 298 over 5.00 equals x over 2. And that works just fine. If you take the inverse of both sides, you guys know what inverse is. Take the inverse of both sides and just flip them. And then that way it's on the top. So now you can multiply by 2, just like we did before. Multiply by 2. And we get 2 times 298 divided by 5. All right. So x is now equal to 119 Kelvin. Okie doke. So now it asks what temperature in Celsius. So now we have the Kelvin temperature, we need the Celsius temperature. So to get it from Kelvin into Celsius, we are going to subtract 273. So 119.2 subtracted by 273 will give us negative 154 degrees Celsius. And that's the right answer. Okay, so that was a lot of fun. All right, so we're going to connect Charles' law to kinetic molecular theory. So we're going to keep something here. Why does an increase in temperature lead to an increase in volume if we have the same pressure? Well, remember that pressure is equal to the force divided by the area. So if we have our three gas particles again, they have some arrows here, and they're colliding with their container. So if we take those three gas particles, those arrows are moving faster now, so now they are going to collide with their container. And to keep the pressure constant, we need to increase the volume, right? We're going to get a greater force. The force is going to increase, but pressure needs to stay constant. So the area must also increase as well. All right, that's tricky to see, but the graph, when graphed, will look like this, and this is known as a direct relationship, okay? Or they're directly proportional, okay? Directly proportional. All right, I'm going to take a break, and then we'll go on and move on to the next part.